All right, let's do an example MO diagram for a coordination complex. We'll talk about ML6, so 6 ligands on a metal, and we'll talk about the sigma-only variation. So these ligands just have the lone pair going in, and we'll treat them as kind of spheres within our MO diagram. So ML6 is going to be octahedral, and then this is in the OH point group. And again, for the sigma only, we just have we can treat them as spheres, so treat them as kind of these guys, donating electrons in. And like I said before, this is you can think of it as a dative interaction, even though there might be some degree of covalency. So treat all of these donors as completely filled. And then so the metal is the Lewis acid in this case. Although the metal, of course, has d electrons, depending on the oxidation state of the metal. So those are the things to keep in mind. So let's kind of start constructing it on the right side here. So here we have our metal, and then we have 6 ligands. So again, keep in mind that the ligands for a sigma donor are always going to be more electronegative than the metal, so they should be lower in energy. So here are my 6. So here are my 6L sigmas. We haven't yet done the sulks. And then on the left side, for our atomic orbitals of the metal, we have our d orbitals. So I'll draw them higher up. So here are my d orbitals, and then we have the s, and then we have the p. And then if you look on your character table under the OH point group, we know that the d orbitals transform as Eg and T2G. So the Eg are dz squared, x squared minus y squared. And then the T2G are xz, yz, xy. And the s transforms as A1G. And then the p orbitals transform as T1U. I'll remind you again that for what's it called? Point groups with an inversion center, we get the G and the U, Garada, Ungarada, for if it's symmetric about inversion or not, respectively. So d orbitals and the s orbital are both symmetric about inversion, while the p orbitals are U because p orbitals do not have symmetry with respect to inversion. Okay, great. And then without derivation, I'll let you guys figure this out on your own for the sigmas. The sulks of the sigmas are A1G, EG, and T1U. I'm off screen. Okay. We can draw those on the right side, or on the left side here. So here's A1G, sulk. This one's the obvious one. They are all in phase. And then our EG looks like so. I think we actually did this as an in-class activity at some point. So these two. And then our T1U looks like our respective p orbitals. Like so, and like so. Okay, great. So those are our sulks, and now we can make our MO diagram. Okay, so again, the key part here, or maybe there are many key parts, but I want to remind you that all the sigma orbitals for your 6 ligands are all filled. And then our d orbitals are filled with however many electrons there are. So for example, let's suppose that we are d3, so we'll have 3 electrons here. And this is of whatever metal oxidation state that you are, metal and plus. Okay, so the reason I mention this is because we can start interacting orbitals. So we know that A1G, EG, and T1U can all interact with atomic orbitals on the metal, right? So we have EG, we have A1G, and we have T1U. So what this means is that these all go down in energy. I won't say where they are because, well, we can if we want to. So here's, and then we have T1U, whatever ordering that is. It could be different. And of course, I'm not going to draw the corresponding lines, or I can if you want, but I will, just because. There we go. We have our EG going down here. We have our A1G here. And then we have our T1U there. And then the reason I'm mentioning this is because these are all filled. And these are all low in energy. So low in energy, filled. Because remember, these molecular orbitals are stabilized compared to the ligand orbitals, and the ligand orbitals themselves are lower in energy than the d orbitals of the metal. So these are kind of low in energy, so we can kind of just ignore them. So they do bond and they are stabilized. So now what matters is kind of these higher metal-centered orbitals for chemistry, right? Because the highest energy orbitals, the HOMO and the LUMO, et cetera, are what matter for reactivity. So now we consider these orbitals. So T2G, as you can see, there's no T2G ligand orbital. So what happens is that that's non-bonding. T2G non-bonding. And then we have an EG, which was corresponding to this EG in the ligand. So EG over here. This is anti-bonding. So this is a sigma star interaction, if you want to call it that. And then the s orbital, of course, A1G, so can interact with this A1G sock. This goes up in energy. This is our A1G star. And then the T1U can also interact with these T1U socks. So these go up, and there we have T1U star. So these orbitals, these three at the top here are all anti-bonding. This one is non-bonding. But these are the orbitals that matter because when we start filling in the highest energy electrons here, we then have our D3 electrons. So what this means is that when we think about a transition metal complex where the D electrons are in the metal, all these highest energy electrons are within this DD splitting manifold. And that's why we can kind of ignore all the ligand-centered orbitals. They're all down there. They're all low in energy. They're filled. And then what changes when we change the metal or the geometry is purely within here. So all these three electrons come from the metal, and they all change depending on what we're doing to this metal center here. And things to keep in mind, this 2 above 3, e.g. T2G, is this pattern holds for all octahedral complexes, so keep this in mind if you can't derive it on your own. So 2 above 3, e.g. T2G. And in crystal field theory, or et cetera, this splitting, this DD splitting matters a lot for spectroscopy. And this is often called delta O. So this O is for octahedral. For other geometries, you might have a delta T, for example. And this delta O, how much this splits, which is basically how much overlap we have the ligand with these two D orbitals, that really dictates your spectroscopy, and also a lot of other factors that we'll talk about later in class. So in class, on Wednesday, we'll do other geometries, and we might also start doing pi interactions with ligands that might have perpendicular p orbitals that can then donate or accept pi electron symmetry density. Okay.